will be taken by Professor R. Balasubramaniam. He had already taken one session for us on the first day, and this is his second session with us. So we are privileged to welcome Professor R. Balasubramanian. He's Professor HAG and Head of the Department of Computer Science and Engineering at the Indian Institute of Technology, Roorkee. He also serves as a joint faculty member at the Mehta Family School of Data Science and Artificial Intelligence, IIT Roorkee. He received his PhD in computer science and engineering from IIT Madras and has since established a distinguished academic and research career. He currently leads the Machine Vision and Intelligence Lab at IIT Roorkee, where he directs cutting edge research in a wide array of domains, including image and video processing, medical imaging, activity recognition, pattern analysis, privacy preserving, and biometric security systems. Professor Bala has authored over 250 peer reviewed publications in high impact international journals and conferences, reflecting his sustained research excellence and scholarly influence. His interdisciplinary work bridges foundational research with real world applications, advancing the frontiers of artificial intelligence and intelligent systems. We are truly honored to have you, sir. And now looking forward to your session. Over to you.
Thank you, Dr. Priyanka, for the introduction again. So, in this lecture, my slides are visible, right?
Yes, sir, it is visible.
Great. So, in this lecture, as I have been given, we will be focusing on the mathematical part of the image processing. So, I have taken the topic information security. Okay, so we are going to talk about two different areas. So one is digital image watermarking that comes under multimedia security. Another one is the encrypted domain processing of multimedia data over cloud. So how mathematics is being used in these domains, we are going to see. So nowadays, our digital world, what we are doing, we are transmitting so many data, right? So much data. The data may be a video, there may be audio or image or a text, right? So now, suppose, right, assume that you have taken a beautiful picture, right? So which fetched, that is $1 million. And how do you claim that that image belongs to you, right? So in the suppose you're seeing the arts, right? Arts of Ravi Verma or any important paintings, they write the names, right? You can find the names or initials in the painting. So in a similar way, the digital point of view, all right. So how do you ensure? Suppose I have taken the image and that image belongs to me, all right? So you have, right, several flaws, right? Illegal copying. Somebody may copy and then they can claim that the image or video belong to them, or they can do some modification and say that okay, that belongs to them, right? And then copyright protection. So you might be hearing this, right, in terms of video or audio, or let us say even in the image, right? And then how do you make a ownership, and how do you identify that you are the owner, right? So these are all some of the digital flaws. So how do you ensure how they have in the literature, they ensure that the data belongs to you, right, or the media belongs to you, or the image belongs to you, right? So for this we are going to talk about digital image watermarking, right? Digital image watermarking in the sense, suppose you have an image, and in the image you will have another image, but that image will not be visible. If it is visible, then you call this as a visible watermarking. All right. For example, we are watching IPL, right? So you have, right, you are watching under Star Sports. So you have the star logo, right? So that means the copyright belongs to the star, right? So like this, when you are seeing the logo is nothing but watermarking. So that means the complete copyright belongs to the Star Sports. right? So this is an example of a watermarking. And in fact, so right, suppose you have an image and I am inserting this particular watermark. For example, here you consider this as a watermark, our IIT, the old logo, right? So now I insert this watermark over this image, and then my new image, I mean to say the resultant watermarked image is like this. So that means this particular logo is hiding behind this, right? So watermarking is nothing but the extension of cryptography, right? The cryptography, what you are doing inside the text, you have another text, or another area, right? You have an image, inside the image you have a text. All right. So here in the case of a watermarking, inside the image you have another watermarking. So this is the original image. You have a watermark, and the resultant image will be like this, the watermarked image. Right. So for example, in our Indian currency, I have taken the old note, right, without loss of generality. And here you can see, right, so you have all types of watermark, right? So you have so Mahatma Gandhi picture over here, which you call it as a visible watermarking. And here you can see the invisible watermarking, right? So in this area, if you look, that is parallel to the roof and perpendicular to the light, you can see 2000 over here, right? Now you take a 500 note. This is the old note, right? You can take a 500 note, and particularly if you see in this part, you can see this 500, right? If it is a 500 note, and here you should see 2000, right? So you call this as a invisible watermarking. So now, watermarking technique. So several authors have used the the spatial domain, and there is too much work the researchers have done in the frequency domain. So frequency domain is nothing but the mathematical transformations. For example, Fourier transform, or fractional Fourier transform, or fractional wavelet transform, discrete wavelet transformation with the singular value decomposition, wavelet packet transform, right? Fractional cosine transform, multi-resolution discrete cosine transform, right? So these are all the transformations along with singular value decomposition, right? Walsh-Hadamard transform, best-to-tree wavelet packet transform. So you can find, in fact, our group has done several work based on the mathematical transformations. So now, how do you classify the watermarking? Let us say non-blind watermark, blind watermark, and semi-blind. What do you mean by this? Right? So, for example, non-blind watermark, you should know everything in hand. Host image you should know, watermark you should know, and then the key generation you know. So then you can extract the watermark, right? Watermark image also should know. Then you are extracting the watermark. So you call this as a non-blind watermarking, right? So blind watermarking. So this is very, right, the tedious job to do. Reason is you will be given only watermarked image and a key. Only this. For example, semi non-blind, you require everything. You require everything, and you are extracting the watermark. Whereas blind watermark, so this is a challenging one. You will be given only watermark and then key. Right? I'll come to you. What do you mean by key? All right. So then you are extracting the watermark. You call it as a blind watermark. And semi-blind, you should know the partial information. Partial information about the host image, partial information about the watermark. Of course, in all the cases, you should know key, and watermark image should also be known. Then you can have the extracted watermark. So this is how it is being classified: non-blind, blind, and semi-blind. Right. So now, where exactly the watermarking concept came? Right. For example, any image can be written in, I mean, or put it in 8 different planes, right? You call it as a bit plane slicing concept, right? So any image that contains a gray level value, assume that, for example, if I consider a 8-bit image, you will have 0 to 255 gray level values, right? 0 to 255 gray level values, 8-bit image. So now any number you take, any digital number you take, for example, assume that I take 50. So what is the binary? Find out the binary, put it in 8 bits. You will have zeros and ones. 255, right? Find out the binary. All right. So like this, when you have the complete digital image, assume that we consider the gray level image, and all the numbers, all the digital numbers, I represent in the 8-bit and put it in the bit planes like this. You call it as bit plane 0, which is least significant, and bit plane 7, which is the most significant bit. For example, assume that this is the image, right? So this is the image. I have taken this image from the famous book called Gonzalez Image Processing, right? It's a fractal image. Now, if I do the bit plane slicing, it will be like this, right? So that means 7th bit plane. What are all ones and zeros? So 1 you consider 255, 0 you consider black, right? 255 is white, 0 is black, or 0 is black, 1 is white. So when I plot this, you can get 8 different bits, right? 8 different planes. All right. If you look at the top one, this is the most significant. Why it is called most significant? You will get certain pattern. You will understand your image pattern will be like this. This is a given image. So pattern will be like this: 8th bit plane, 7th bit plane, 0, 1, 2, 3, etc. 7. 7th bit plane, it is like this. 6th bit plane, it is like this. 5, 4. When you keep on going, if you look at 0th bit plane, you find the noise kind of. Right? So this is not more significant image. Right? It is very clear. Only information you can find, it is a circle in shape. Otherwise, no information. When you compare to 7th bit, it has a enormous information. Right. So now what I will do, I will take only 7654, only 4 bit, the top 4 bits, right? Top 4 bit planes. So when I combine this and keep all these 0, all right? So this one 0, this one 0 means black, right? 3, 2, 1, 0, complete black. All right. So then I will add only 7654, right? I will add only 7654. So then in that case, you can find, so this is the original image, right? The left hand side is the original image, and right hand side is the image you have reconstructed from 7654 bit, right? You can almost find no difference. The human vision cannot find any difference between these two, almost. But when I subtract, this is the subtracted values, right? When I subtract a minus b, I will get this, right? So now where the watermark is starting, right? So when you look at here, all right, when you look at here, when I make this 3210 as complete 0, all right? So completely I'm making 0. So that means these informations, at least this information, right, I am making, let us say, some text. I will add some text. Exactly this number of data, let us say k bits. So less than k bits, I can use it for 0, 1, 2, 3 bit plane. Let us have some text. All right, let us have some text. I insert it in 3210 because I made it everything 0. All right, so 3210 plane, I'm making some text, and then I'm reconstructing my watermark, right? So nobody can find out what exactly you have inserted. Correct? It will be like exactly like this, and additional data. Whatever the data available here, let us say k bits. All right, very least significant. So these least significant k bits I use for some other data, some other information. Let us say some text. All right. So this information I'll pass from one place to another place. This is how exactly people have done, right? In, let us say, 1970s or 1980s. When I want to pass the information, so I'll make 3210 bit plane completely 0. so that whatever the data, for example, this is the data, unwanted data, kind of, and then I remove this, put some, right? Same k bits, I use something. If you use a text, you call it a steganograph. If you use an image, some other image, right? Assume that instead of this image, I use some other image. Whereas the number of bits should be maximum the same size. K bits means maximum k bits, and then reconstruct it, right? So that means it is going inside, so nobody can be able to decode that, right? So that was an idea, but unfortunately, right, we have to always worry about intruder till today, right? No digital transactions are safe, right? Every day we are getting the news, right? You have to be very careful, or when you are doing a transaction, somebody may hack, right? We have to worry about the hackers, right? So the hackers, what they do, they find out from 3210 plane, and then, right, they can get the information. That was the problem with the spatial domain. So the people have moved to frequency domain, right? So frequency domain. So immediately you can think of, let us say, Fourier transform. Time domain, if I go to the Fourier transform, right? E power minus I psi t kernel, right? So when I go to the Fourier transform, I will have a, right, low frequency band and high frequency band, right? So exactly similar to this. The low frequency band is equivalent to the 3210 plane. So what I will do, the low frequency domain, I'll completely make it zero and put some information. And then take the inverse Fourier transform. I call it as a watermarked image. Again, there is a problem in Fourier transform, right? So the hackers will concentrate on the low frequency component, right? The low frequency band. Then there is a possibility that you may lose the information, or the information can be hacked. All right. So how do you solve this problem? So I introduce now the fractional Fourier transform. Right. So what do you mean by fractional Fourier transform? Right. So here we are going to propose an algorithm based on fractional Fourier transform. Right. We will see the mathematical part, and then we are going to see singular value decomposition. Right. So based on this, we propose the algorithm. Right. So here you go. If you look at the kernel, your Fourier transform, it is very simple, right? You have a e power minus I psi t or IUT, right? I'm using k alpha of t comma u, k t u. So e power minus I t u. Kernel is very simple in the case of Fourier transform. But whereas if you look at the kernel in fractional Fourier transform, so this is a kernel. It is defined like this, right? Highly and nonlinear equations. So now physically, we will analyze this fractional Fourier transform. For example, this is the original signal. Let us consider a one-dimensional case, right? So this is a signal, and when I use my alpha, the fraction, right? Here the kernel is k alpha tu, right? So when I use alpha is 0.01 pi, I can see the changes. This is the original signal, and when I use alpha for this particular, right, a mathematical expression for fractional Fourier transform. So here I use alpha as 0.01 pi. Right? So then I will get the output like this. Right? You are seeing the output. There is some change in the signal. And when alpha is 0.05 into pi, you can see the major change. Right? And when you keep on going, when alpha is equal to pi by 2, right, it becomes Fourier transform. Right? So this is a fractional Fourier transform. When alpha becomes a particular case pi by 2, this is your Fourier transform. So the fractional Fourier transform is a superset of Fourier transform. Right? Fractional Fourier transform is a superset of Fourier transform. So when this alpha becomes pi by 2, fractional Fourier transform becomes the ordinary Fourier transform. So now you can visualize how fractional Fourier transform is. Right? So maybe we'll take one more example. Image. So in the case of an image, you have alpha x and alpha y. One-dimensional case, you are taking alpha. And two-dimensional case, let us assume you have alpha x and alpha y, x-axis and y-axis. right? Alpha x, if I take 0.15 and 0.3, my fractional Fourier transform will be like this. If I take alpha is 0.1 and 0.05, alpha x, alpha y, and you can see the Fourier transform is completely changing. And when alpha x become 0.5 and 1, right? So that means for different value of alpha x and different value of alpha x, your Fourier transform or fractional Fourier transform is completely changing. And we know that set of real is uncountable. You have r squared, right? So I can pick any number, right? This is the key, right? I talked about the key, right? When you discuss about the invisible watermarking, etc. Yeah, here we have a key, right? And now if I choose one number, alpha x one number, alpha y another number, only I know that, right? So that is a secret information. You call it as a key. Assume that I choose 0.15 and 0.3 or any number you choose, 0.9 and 0.85, right? Only you know this number. You are not giving this secret information to anybody else. So that means, suppose if I choose 0.15 and 0.3, I am going to work on this particular transformation, Fourier transformation, fractional Fourier transformation. So intruder, what they do, they make guess only, right? What is the number you have chosen? So suppose if the guess is 1,1, they will end up in this transformation. Then they will be completely wrong, right? They cannot able to decode the information, right? Or extract the information, right? So that is the advantage of fractional Fourier transform. So it has more security, right? So that means I have chosen the key, but I can share the key only to my friend. Whenever you want to decode something or you have to extract the watermark, use, let us say, 0.15 and 0.3. So that means when they want to extract, they will try to work it out with 0.15 and 0.3. So intruder, it's very difficult to guess the number, right? I mean, the set of real numbers, uncountable. You can choose whatever you want, right? And then that will be the secret key. That is the major advantage of the fractional Fourier transformation. And another mathematical property is singular value decomposition, right? So any matrix can be decomposed as USV transpose. What is S? S is nothing but the singular value, right? So you are given, right, X, the given image. Assume that I'm finding X transpose X. X may be a rectangular matrix, but X transpose X is a square matrix. So in this square matrix, let us find the eigenvalue and eigenvalue initially, right? Once I find the eigenvalue, I find the square root of the eigenvalue, modulus of the square root of the eigenvalue. So then I write those eigenvalues in descending order, right? So let us write those in descending order. Rest of them are 0. So lambda 1, in fact, you call it as a singular value. Sigma I. Sigma I is square root of lambda I, right? Square root of modulus of lambda I, right? That means eigenvalue, the square root of the eigenvalue, right? The last class we talked about PC and LDA eigenvalue problem. Again, similar, right? So once you find out the eigenvalue, find out the square root of the eigenvalue. The square root of eigenvalue is considered as singular value, and those singular values should be written in descending order, right? So rest of the entities are 0. So only main diagonal you have the numbers. They are nothing but the singular values. Rest of them are zeros, right? So now you find, yes, I found. Now you find eigenvectors. All the eigenvalues, find out the corresponding eigenvectors, right? So once I find the eigenvectors, assume that for a V transpose I am writing. So eigenvectors, you know, they are orthonormal to each other, right? So here, this is an orthonormal matrix, right? The eigenvector I am writing, let us say column, and then I take the transpose, V transpose. So X you know, yes we know, V transpose also we know, then you can obviously find U, right? X into S inverse into V transpose inverse will be U, right? So this will also be orthonormal matrix. So any M cross N matrix, you are divided like M cross N, and singular value matrix is n cross n, and eigenvalue, eigenvector is also you are writing n cross n, eigenvector, right? Eigenvector or the normalized vectors. All the vectors are orthonormal to each other. So any matrix can be decomposed like this, U S V transpose. Okay. So now we are going to use this property, and then we are going to make a key. Already we made two keys for alpha x and alpha y in fractional Fourier transform. And here also we can make some keys, some more keys. So what we can do, take a original image, find out the fractional Fourier transform. Right? So we discussed about the fractional Fourier transform. Right? Find out the fractional Fourier transform. And then once you have a fractional Fourier transform, you divide this into non-overlapping blocks. How do you define? So for example, original image is capital M cross N. Right? Original image is capital M cross N, and watermarked image is small m cross N. So take M by M. Take a floor of it. Right? Or seal of it. Right? In fact, floor of it. M by M, floor. Right? Capital M divided by small m. Similarly, capital N divided by small n, take a floor. Seal and floor. Floor function, seal function. So capital M by small m. M cross n. Capital M cross n is the original image, and small m cross n is a watermarked image. So capital M by small m, take a floor out of it. Capital N by n, floor out of it. So now I can divide based on this m by m. Let us say m dash, n by n dash. Right? So m dash and n dash matrix, that is a non-overlapping blocks. All right. So now find out every block, find out the singular values. You know how to find out the singular values. Right? You use a SVD. Every block you can use a SVD, not a problem. Right? X matrix can be divided into USB transpose. So now every block you take the largest singular values or largest eigenvalues, right? Eigenvalue is nothing but, singular value is nothing but square root of eigenvalue. So largest singular value you take for each block. All right. When you put that, that will be an image. All right. When you put it as a matrix, that will be image. You call it as a reference image. And then you have a watermarked image. So now I am going to embed these. Some alpha into reference image plus watermark. All right. Some alpha. That is the watermark strength. Right. If I am not adding anything, right, let us say alpha is 0. Right, let us say alpha is 0, then original image is a watermarked image. Correct? So now alpha into reference image plus watermark image, I am going to embed this, right, using SVD, singular value decomposition. So I will have the watermarked image. Right? So before that, you will have, because you have done alpha reference plus watermark, you call it as watermarked reference image, and then you have to go back. Whatever you have done, go back the reconstruction kind of. Right? So that means you find out the blocks, each block, whatever you have done, do the opposite way. So each block you find out the singular value. Now singular value might be changed. Right? In fact, it will be changed because you have done alpha into reference image plus watermark. So here alpha is the watermark strength. Correct? If alpha is equal to 0, you have not added any watermark. If alpha is tending to 1, your watermark strength is very high. It's a visible one. All right? It is a visible watermarking. So try to take alpha as much as possible tending to 0. Then do the reverse process. Right? Starting from here, do the reverse process. Right? So when you do the reverse process, you will get the watermarked image. Right? So how it works, for example, you have image, this is the original image, and this is the watermark, CVSS lab of University of Windsor. Right? When I add this with this algorithm, right, when I add this watermark with respect to this algorithm, you can see this is a watermarked image. So now the question is, can you make out any difference? The answer will be no, right? And then I can extract the watermark, right? Extracted watermark. You know how you are extracting the watermark from this algorithm. Okay. So this is how the watermarking is working. So now I want to compare. So this one is the original image and this is the watermarked image. So when I want to compare, I use peak signal to noise ratio, PSNR, right? If PSNR is greater than 28, the human vision cannot differentiate which is the original image, which is the watermarked image. So when you are making an algorithm, make sure that your PSNR is going beyond 28, right? For example, here, right? Obviously, that will be greater than 28. So human vision, so this is a original image and this is a watermarked image. And the human vision cannot distinguish these two images because the PSNR will be greater than 28, right? And then the cross correlation, right, between the watermark, right, original watermark and extracted watermark, how far they are, right, true. For that, cross correlation is being helpful. So now, when you suppose assume that in the childhood you are buying a book, right, in the school, what immediately you will do? You will write it in the first page your name, right? That is obvious. Suppose I want to steal the book, what I will do? I'll take out the first page, right? Remove the first page, trash the first page, and I can claim that the book belongs to me, right? But if you are very smart enough, you are writing right inside the pages also, right? For example, 50th page, 100th page, or somewhere, right? I'll keep on writing my names. So that the idea is I'm securing it more. So in a similar way, so suppose, assume that in this image, right, like writing in the page number, middle pages, I use some average filter. In this is a watermarked image. Assume that I use some average filter, right? Put it some average filter. So when I do the average filter, my image changes, but I can able to retrieve my watermark. When you do this, yes, fine. So that's what exactly you are doing. Secure it. Write your page number. Right in the middle of the page numbers, you are writing your name. That means book is yours, right? So I have to make a proper algorithm. Even if somebody is, let us say, claiming that after applying the average filter, that image belongs to him or her, I can able to extract the watermark. So your algorithm should be like this. For example, median filter, I can able to extract the watermark. Gaussian noise addition, I can able to extract the watermark. Right? Next, JPG compression. Your algorithm should extract the watermark. So like this, these are all nothing but the geometrical attack. Right? The intruder is trying to say that this image belongs to him or her. Right? So in that case, you are beating them by finding out the watermark. Even 90% of the image is being cropped. Still, I can able to extract the watermark. Right? Resize. After resizing the image, extract the watermark. After rotation, extract the watermark. Histogram equalization, extract. Right? So like this, so many geometrical attacks are there. I can able to find out the extracted watermark. Once you are getting the extracted watermark, you can find out the cross correlation. CC stands for the cross correlation, and you can find that, right? So one is the maximum, right? One, in fact, one, if you get correlation one, your algorithm is good, right? In that case, whatever the extracted watermark is matching with your original watermark. Okay, so that is what the idea we are getting. So for different attacks, different geometrical attacks, so you can see the changes in the cross correlation. Right? So you have several. The one I talked about, Fourier transform, fractional Fourier transform. So you have several papers, right? So these are all the old work, all right? So where we have done. So here it is, discrete wavelet transformation with the singular value decomposition. discrete wavelet transform, and SVD, another mathematical part. So we talked about fractional Fourier transform and SVD. So you can find discrete wavelet transform with SVD, right? So these are all the concepts where we can secure the data. So you call it as the information security. And in the next part of the talk, I'm going to talk about the encryption domain processing, right? Encrypted domain, we are going to do the image processing. All right. So yeah, we'll have a slight little break. I'll take some water, and I'll continue with the encrypted domain processing. So we'll meet in 2 minutes.
Hello.
Priyanka, I'll be continuing.
Yes, sir. Yes, sir. Yes, sir.
Hope I'm audible.
Yes, sir. Yes,
Okay,
sir.
thanks. So the next topic is encrypted domain processing, right? So what do you mean by encrypted domain processing? So I mean, it is obvious you're seeing a 10-year-old paper, right? Here, we know that when we are doing a image processing, you're given an image, you are doing some right enhancement or restoration or applying some mathematical transformation, and you're getting output. So now what we can do, so instead of dealing the images directly, assume that I put all these information in some cloud, right? I'm sharing it. For example, assume that I have n clouds, right? One image is there. I put them as a share. So assume that I want to do, let us assume I want to find the number plate detection, right? So it's a usual problem, right? Very standard problem. Given image, you can find the number plates. You may ask the question, what is the grade in it? What is grade in it? But now the question is, when I am keeping this vehicle in the cloud, right? In the encrypted way. The encrypted way, the images look like this. In the cloud, you can see two images, right? These are all the encrypted images. I don't find any information. I don't know anything, right? If you are given the images like this, let us say two clouds, C1 and C2. All right. Now the question is, if your encrypted data is like this, is it possible to determine the number plate? A challenging problem, right? So encrypted data, I will try to get the information like this, and then I have to reconstruct to get back my data, right? Which is a very challenging problem. All right. So I have encrypted data, and then I can find again, let us say, the number plate equivalent to the encrypted data. From those encrypted data, I am trying to find out what is the number plate, right? Which is a very challenging problem. So this work appeared in ACM Tom, right? So this was an idea, and how do you do the encryption? The mathematical part, right? So let us consider a Shamir secret sharing algorithm, right? So here it is like a polynomial, a naught plus a1x plus a2x squared plus a3x cube, etc., etc. Let us say I consider, right, the n minus 1 or k minus 1 polynomial, right? And then mod p is a prime number, right? So let us assume I have a secret number. So in an image, let us consider one particular gray level value. Let us say the number is 100. All right. So the number is 100. I am trying to make a polynomial, the polynomial like this, and mod p. So these AIs, A0, A1, A2, etc., AK minus 1, we are randomly choosing between 0 to P minus 1, where P is a prime number. Right? So let us take one example. For example, all right, then we will come back to the reconstruction. Right? I will come back to this particular slide. So let us assume 100 is a secret number. All right? And 251 is a prime number. I am going to generate 4 different encrypted values for this 100. Right? So when I have a polynomial, without loss of generality, we considered the straight line a0 plus a1x. Right? You can extend it a0 plus a1x plus a2x squared if it is a parabolic, or you can go for a cubic, put a3x cube, something like that. Right? So now for the understanding, we consider a straight line 100 plus 19x. All right? I can choose a1, a2, etc., ak over minus 1 between 0 to p minus 1. The prime number we have chosen 251. You may ask the question, why do I choose prime number 251? If you look at the gray level value 0 to 255, right, between 0 to 255, 251 is the largest prime. That is what an idea. So now in the sum is secret, I have 100 plus 19x mod 251. Right? Put x is equal to 1. All right? 119 mod 251. 119. X equal to 2, x equal to 3, x equal to 4. So you put whatever x you want. I have, just for your understanding, I take this particular example. You put whatever x, put x equal 10, and then mod 251. You will get a number. Right? So now what happens? Your original number is 100. Right? But I am making 4 shares, the meaningful 4 shares, because of this 100 plus 19x polynomial value. Right? Polynomial. I am making, right? First share I have 119, 100 becomes 190. Second share it is 138, 157, 176. Since we have taken the line, right? Straight line, your number is like this. You take any other polynomial, right? You have a choice of having a0 plus a1x plus a2x squared, etc. Correct? Now, assume that you have 4 cloud. Your number 100 is now 119 in one cloud, 138 in another cloud, 157 the third cloud, and 176 in the fourth cloud. Right? Now the reconstruction. The reconstruction is based on the Lagrange interpolation. So now the question is, whenever you have a cloud, is it necessary that all are up, right? Assume that 2 out of 4, right? 2 out of 4 are up. Not all are up. 2 servers are down, 2 cloud servers are down, and 2 are up. 1 and 4 are up, right? So is it possible to reconstruct my original value from 1 and 4 only? I don't have any information about 2 and 3. Assume that the server 2 and 3 are down, right? So now I apply the Lagrange interpolation. I have the number 176, fourth and first. Apply this, right? Apply this formulation. Get back, right? So what I am getting back, my secret value is 100, right? So this is how the Shamir secret algorithm works. It's a very famous algorithm, right? So Shamir secret algorithm. And the second one is, many of you might have learned in your discrete mathematics or those who have done a number theory, Chinese remainder theorem, right? So Chinese remainder theorem, so the theory goes like this. Suppose I have a secret value 100, and then I use three prime numbers, M1 19, M2 29, and M3 31, right? So first I found the residual numbers, Ri's, R1, R2, R3. So simply I put 100 mod 19. 19 is my first prime number. In fact, this 3 should be relatively prime. Yeah, when you take all our prime numbers, obviously they are relatively prime. Right. So now when you look at residual numbers, I calculate 100 mod M1, 5, 13, 7. Right. So now I have the secret information 5, 13, 7. So like this you can generate, all right, whatever number you want, because you choose the prime numbers and then you choose the residual numbers, right? So the secret information now, the residual number is 5, 13, and 7. That means 100 now became 5, 13, and 7, right? So like this, assume that I have 3 shares, right? Like this you can generate as many shares you want. So 3 shares, right? So now how I can reconstruct my values, right? Now your 100 became 5 in one cloud, 13 in another cloud, and 7 in the third cloud. So from this information, is it possible to reconstruct? Yes, it is. All right, that is how the Chinese remainder theorem works. 5, 13, 7. And when you multiply all, you are getting 17081. And then when you are solving the congruences like this, M1 cross M2, M2 cross M3, right? M3 cross M1, right? So find out those values, and then the idea is to find out MISIRI, right? Already you have the residual values, right? And then when you solve these congruence, 3 equations are there. When you solve these congruences for S1, S2, S3, you can find S1, S2, S3, and already you know what is M1, M2, M3, right? M1, M2, M3, M1, capital M1 is defined as M2 cross M3, M2 is defined as M1 cross M3, and M3 is defined as M1 cross M2. So you have found out M1 and S1, and R1, R2, R3. We have already have the secret information 5, 13, 7. And when you substitute all these, mod M, capital M is 19 into 29 into 31. That means multiplying all the prime numbers. And then when you solve this, you will get back the secret value, right? Which is the famous Chinese remainder theorem. And the third one is the interesting perturbation of binary, POB, right? Suppose I have n is equal to 9 and R, let us say the digits are equal to 4, right? So suppose the given value 33, right? And then I am choosing certain binary like this, right? And the corresponding decimal value for B, right? This is the B I am choosing. Corresponding decimal for B, when I am converting into decimal, it is 116, right? Now, how do you apply this POB? For example, n equal to 9, R equal to 4, and value is 33, right? So R is nothing but how many ones you have in that binary. For example, when I say R equal to 4, you can find 4 ones. All right. Rest of them will be 0. All right. That is what R equal to 4 and B is this. So let us say when you output should be this, right? Input is n is equal to 9, R equal to 4 and value 33. My binary is this. And when I'm converting that binary into decimal, that is my secret. Your original value is 33. I am finding this. So how do you find this? I choose, suppose B is all zeros, right? Assume that all are zeros. Then you have n is equal to 9. I'm copying this into J, right? And value I'm copying into temporary value, that is 33, right? So I have to go one by one. K equal to 4, right? When K is equal to 4, I am finding JCK, 8C4. 8C4 is 70, which is greater than temporary value. Whenever it is greater than the temporary value, put 0. Right? When it is less than temporary value, put 1. Right? Now J will be reduced to 1. That means J minus minus 7. 7C4, 35, greater than 10. So that corresponding 7th bit, I can say 7th bit. 8th bit was 0, 7th bit is 0. So you keep on computing this. All right, 7C4. Then 6C4, 15. 15 is less than temp. Temp is 33. When it is less than temp, put that particular value, bit value is 1, and temp will be reduced by P, temp minus P. Right? So P is 15. Previously temp is 33. 33 minus 15 is now 18. Right? Your temp is, new temp is 18. All right? So then you stop it. And similarly, go for K equal to 3. All right? You are going one by one. K4, stop it and put K equal to 3. Again, continue. J equal to J minus 1, 5C3, 10, less than 10, put B5 is 1. So when you keep on doing this, all right, you can check how the algorithm works. All right. And then if you look, whatever you have found out in B1, B0, B1, B2, B3, etc., put it, and then you can find this is your binary. Right? So you are using the algorithm based on this, right? JCK. And then when the value is less than 10, put again J minus 1K. And then again J minus 1K. So keep on doing this. You will find the binary. And this binary is nothing but when you are converting into the decimal. For example, in this case, the decimal equivalent is 116. So that means your original value 33 will be converted into 116 in the cloud, or the encrypted value is 116, right? So this is how permutation of binary works. So the first two algorithm is a homomorphic algorithm. The last one is a non-homomorphic algorithm, right? So now you can, I will share this slide and then you can find how you can able to reconstruct. All right. So you are given this binary or 116, convert into binary, n equal to 9 and r equal to 4. You can able to reconstruct. P naught is defined as summation of bi, right? And initially P naught you are considering I is running from 0 to 0, which is equal to 0. So find out, right? So P1 will be I is equal to 0 to 1 bi. So that means B0 plus B1, right? Which is equal to 0. One can find based on this expression. And similarly P1, P2, etc. Right? P0 0 to 0. P1 is summation of 0 to 1. That means B0 plus B1. So you have all, right? B0, B1, B2, B3, etc. Whatever be the last one, right? So when you keep on finding this, I will end up P0 is this, P1 is this, P2 is 1, so on. Right? So now when I do this, right? So 2, 1, I am finding first. So when I find 2Z1, here you go. Right? When I'm substituting over here and then add everything, I will get back my original value 33. So that means suppose your secret number is one, sorry, your cloud, that means encrypted value is 116. Corresponding binary is nothing but capital B, and n is the length of the string, and r is number of ones. When this information is given, what is your secret value? The secret value is 33, right? So this is a third algorithm, right? So now what exactly you can do, right? For example, the usual image processing algorithm, suppose I am using, right, I am applying some filters, right? So the proposed algorithm, right, here you go, right? So suppose this is an image, I can make two shares, right, based on, let us say, Shamir's secret algorithm, right? So let us say Shamir's secret algorithm. So it's a given image and I have two shares. All right, these are two shares. And permutation of binary, I have four shares. So from this, is it possible to reconstruct an image? The last one is a reconstructed image. So that means in the cloud, you will have the information like this. Right? So Samir's secret share, if you see, it is giving a partial information. Whereas the permutation of binary, the black images, is just a share. You can't make out anything. So your algorithm should also be like this. Right? So now I can either combine all the four, all the three, or only two. Is it possible to reconstruct? Yes, it is. Right? So in fact, we had seen Shamir's secret algorithm, two clouds were down and two were up. So is it possible to reconstruct? Yes, I can get my number back. Right? So this is how the algorithm works. So similarly, when you apply for the filter, this filter, the usual image processing algorithm, plain domain in the sense, image processing algorithm, I apply the disk filter. Usual image processing algorithm, after applying a disk filter, my resultant image is this. Now in the encrypted domain, how far they are matching. Similarly, Gaussian filter, apply Gaussian filter for the usual plain domain and then encrypted domain. Right? And then with the help of histogram, you're checking how far your results is matching with the usual image processing algorithm and the encrypted image processing algorithm. Right? So this is how the encrypted image processing algorithm works. All right? So you have an image. These are all the shares. So from these shares, is it possible to reconstruct the images back? All right? So you call this concept is the encrypted domain processing, right? So you can go through. There are several examples based on this. All right? And then the main thing is you have to compare this with your usual image processing algorithms. So encrypted domain, you got the result, and the usual image processing algorithm, you got the result. How far they are matching. So the comparison of the enhancement algorithms or encryption algorithms, right? So you can have, see, for example, if you look at the title, color me, store me, know me not. So without knowing the image, can I do the coloring? Can I store the information? Right? So for example, you have a source image and then target image. So I have to do the color transfer. So color transfer, I have to do in the encrypted domain. So you have an image, you have the encrypted images. So in the encrypted images, you have to do the coloring, color transfer, right? So same, if I divided into three cloud shares, right? So CDC, the cloud data centers, right? So here, suppose I have a source image and I have a targeted image. So the usual image processing algorithm is not a big deal. But the question is, suppose it is a encrypted domain, right? How your algorithm works. So that is a big challenge. All right. So these are all some application scenario. So source image, it's a target image, and then you can see. All right. So suppose I want to combine these two, stitch. right? Encrypted image processing stitching. Similarly, we have done some work on the video as well, right? So the video tampering detection, right? So with the help of the concept encryption, is there any tampering? For example, somebody may add some content in the video, right? How do you determine this is the added content, right? So this we can do with the help of the encrypted algorithms. So in that process, in our research group, so you can see so many right work we have done on this particular right encrypted algorithms, right? So completely mathematics. So three different algorithms we have seen, and in fact, if you look at our work, I mean there are several other encryption algorithms as well. Not only these three, so there are several other encryption algorithms. So these are all some of the relevant publications, and in particular one of the areas, right, the medical imaging. Suppose this is a patient and this is the image, medical image, and of course in the case of a medical field, you should not disclose the person and the disease, right? So in that case, when I put all the information in the cloud, right, so one is, let us say, A is the cover image and B is the secret information, right? And then I want to use both watermarking concept as well as encryption concept. So these two we have studied today. So with the application point of view, right? So secret information, and this is a cover image. A is the cover image, B is the secret information. And then now from the cover image, I can take the shares, right? So C is nothing but this is a C, share of the cover image embedded with secret information. So now I use the watermarking algorithm. I put the secret information here. So D and E, this is D and E. These shares contains only cover image information. So the share of the cover image. C is what? Share of cover image embedded with the secret information. So share, and then I have embedded the watermark over here. And this is simply the shares of the disease image. So now, so we know that we have done a watermarking algorithm, we know the sharing. So is it possible to get back the information? So now in the cloud, you will have only CDE information. I'm putting the CDE information only in the cloud, right? So is it possible to reconstruct? Yes. So with the help of watermarking reconstruction algorithm, with the help of reconstruction from the secret information, right? That means the encrypted algorithms, I can able to get the original cover image and the information. So this is one of the applications in the medical domain, right? So if you have any questions, so we talked about watermarking algorithms, we talked about the encryption algorithms, and we have seen several applications out of it. And the last application I told in the medical imaging, you will have both the algorithms combinedly when you work. That means you can have a watermarking, you have encryption, so combine together and put them in the cloud, right? And from the cloud, I can able to reconstruct as well. So the last two images are the reconstructed or extracted information. Okay. So if you have any questions, please.